Welcome to a mind-blowing journey into the heart of the atom, the nucleus. In this video, we'll explore how tiny particles unleash enormous amounts of energy through fusion, fission, and radioactive decay. Get ready to uncover how the nucleus powers the stars, shapes the elements in our universe, and even fuels modern technology. This is nuclear physics. So far in quantum mechanics, we've spoken about electrons and photons, but we never actually talked about the particles inside of the nucleus itself. The nucleus contains protons and neutrons that ultimately make up the positive charge that causes for electrons to orbit around the nucleus. Protons and neutrons are called nucleons because they are contained within the nucleus, and the proton and neutron both have mass that is about the same to each other, but much larger than that of an electron. The proton has a positive charge of plus the elementary charge value, and the neutron is neutral. The nucleus ends up being about 1/100,000th of the size of the orbit of a total atom. So really, the nucleus makes up a very small portion of space of the actual atom. And finally, there is a spin value associated with protons and neutrons. They also can have a spin of 1/2 value, just like the electron. To keep track of a particular nucleus, we will use Nuclide notation, which is a way of denoting which element we're talking about and how many protons and neutrons are in the nucleus of that nuclide. Here, X is the chemical symbol from the periodic table. Z is the proton number or the atomic number. This can be also taken from the periodic table. And A is the mass number, which is the sum of the number of protons plus the number of neutrons. Sometimes we'll use capital N to keep track of the number of neutrons, but really that doesn't need to be shown because the mass number minus the atomic number should tell you how many neutrons are in that nucleus. For this example, you see that we have carbon 12 that's got an atomic mass number of 12 with 6 protons, and so we can keep track of the element C as its chemical symbol. 6 is the Z number for the number of protons in that nucleus, and 12 is the mass number for the number of nucleons in that nucleus. Now, it turns out through particle physics experiments, we are able to determine that mass and energy are actually equivalent on this small scale. That should feel a little bit weird, but Einstein postulated that E is equal to mc squared. There's an energy associated with the mass of a particle itself. And if I can break that particle, if I can break the nucleus of a hydrogen atom apart, I will release some energy. And this is the idea behind the atomic bomb or nuclear reactors that are used to create energy. So ultimately, we will present our masses usually in atomic mass units, AMUs, unified atomic mass units, which has the letter U. Sometimes this is also called a Dalton or a DA. And ultimately, this is a very small amount of kilograms. Atomic mass units are on the scale of masses that we need for the nuclear physics experiments that we're going to talk about. And these are very small amounts of kilograms. But according to Einstein's postulate that mass and energy are equivalent, we can also say that mass is equal to energy divided by c squared. C squared is the speed of light. And so one atomic mass unit U can be said to be equal to 931.5 mega electron volts per c squared. And now we do know a number for C. It's 3 × 10⁸ meters per second, but just for a moment, go ahead and make sure to leave c squared as its own unit. Do not multiply it out. Just leave it as its own unit. You'll see here for this mass, I presented this number as 931.5 mega electron volts per c squared. And I didn't divide by c squared or anything like that. I just left it exactly as it is. So the mass of a proton and other subatomic particles are given in this table here. And you'll see for a proton that its mass is technically slightly different than that of just one atomic mass units. It's 1.007276 U. And we can say that that is equal to a mass in MeV per c squared, mega electron volts per c squared of 938.27. So for these numbers, we're talking about very small masses to very fine precisions. And you will want to make sure to include as many decimal points as you can in this unit when you're given numbers like this to a very high precision. Do not round these numbers. Plug them in exactly as you see them into your calculator. Different nuclei can vary in their structure and how many protons and neutrons there are in them. The most common type of nuclide variant is an isotope, which has a different number of neutrons but the same number of protons. This is essentially the same element that is just a heavier version because this nucleus has one extra neutron in it as compared to the neutral, most stable, naturally occurring state. So for hydrogen, we could also have isotopes of deuterium, which has one neutron rather than zero, or tritium, which has a number of neutrons that is 2 and 1 proton. We could also have isobars, which is another form of nuclide. This is essentially different elements that have the same mass number, so you can see some examples right there. Or we could have nuclear isomers, which are the same element with the same number of nucleons in there, the same mass number, the same proton number, but the nucleus itself is in a higher level quantum state. Even the nucleus itself can become excited as if in the center of that nucleus it has a lot of energy. And so isomers are nuclides that are the same but in different energy states. The size of the nucleus is essentially related to the number of nucleons in the nucleus. Basically, protons and neutrons are right around the same size, and they're all being squished together into the center of an atom. And so we could estimate the size of just the nucleus itself, excluding the electron orbiting around the atom. Just the nucleus itself, we could calculate its nuclear radius by taking R0 times the mass number raised to the 1/3 power. Here we see R0 is a constant value of 1.2 femtometers. These are very small scales, 1.2 times 10 to the minus 15 meters, and that's the radius of just a single proton off on its own. So as I add in more and more protons, essentially the way that this nucleus gets larger is proportional to A to the 1/3 power. But something should feel a little bit weird here. We have positively charged protons all stuck together at a very close distance with only negative or neutral neutrons in between them. So according to electrostatics, we would expect for these positively charged protons to repel from each other. In fact, they're so close to each other, we would expect for them to repel a lot. But it turns out there's a new type of force called the nuclear force, which is like the glue that holds a nucleus together and prevents it from breaking apart due to electrostatic repulsion. This strong nuclear force, we surmise, must be there in order to keep the nucleus glued together. And so this strong nuclear force counteracts the electrostatic force to ultimately create a low point in the potential energy graph where the nucleus is stable at a certain sweet spot. All right, so let's take an example and let's look at an iron nucleus. This has a mass number of 56, and from the periodic table, sometimes it won't show you what the Z number is, but we can look at the periodic table and determine that it has an atomic number of 26, so that is the Z number for this nucleus. We're asked to find the nuclear radius and the density of the nucleus itself, assuming a spherical volume for that little ball at the center. And we're going to assume a mass number of 56. That's the protons plus the neutrons in this nucleus. So to calculate the nuclear radius, we will take R, multiply R0 times the mass number to the 1/3 power. So here we'll go ahead and calculate the radius of the iron nucleus. And so for the radius of this nucleus, I'm getting a value of about 4.6 times 10 to the negative 15 meters. That is very small, much smaller than even the orbit of the electron around the atom itself. The nucleus only makes up a very small volume of the actual atom. And now to calculate the density of the nucleus itself, we assume that it is a sphere with a volume of 4/3 pi r cubed, and we know that the nucleus has a mass that we are given here in atomic mass units. So let's calculate that density. It has 56 U as the mass for just the nucleus itself, dispersed over a volume of 4/3 pi r cubed, where R is that number that we just solved for, 4.6 femtometers, or 4.6 times 10 to the negative 15 meters. And that number needs to be cubed for the volume of a sphere. And we'll notice that we're in atomic mass units here, and we'll have atomic mass units divided by meters cubed, but we want to get our density in kilograms per meter cubed. So we can convert atomic mass units to kilograms by using the value from the table in the previous slide, 1.66 times 10 to the negative 27 kilograms in every atomic mass unit. So let's see what we get. So for my density, I'm getting 2.3 times 10 to the 17 kilograms per meter cubed, which is extremely dense. The nucleus is very dense because it's such a small volume that that mass is distributed over. And so really most of the rest of the atom where the electron is orbiting is empty. All the mass is located just in the center, which is a very small volume of space at the center of the atom. So the strong nuclear force is a force that acts over a distance to bring nucleons together. It's the glue that holds this nucleus together. And ultimately, this leads to an energy being associated with binding the nucleus together. Ultimately, we find in doing our experiments that the nucleus actually weighs a different amount than the weight of the individual protons and neutrons that make up the nucleus. This is a strange result, but ultimately the mass defect, delta M, is used to track the difference between the mass of the nucleus versus the mass of the protons and neutrons that make up that nucleus. And we find that those numbers are different. We can calculate the mass defect with this equation here, which ultimately takes the number of protons Z times the mass of an individual proton plus the number of neutrons N times the mass of an individual neutron. It takes that number and subtracts the mass of the nucleus that we actually measure, and we find that there is a difference in those two masses. There's a mass defect associated with binding the particles together. Now, it's important to note that in this equation, we're talking about the nuclear mass here. That's just the mass of protons and neutrons, and that's what makes up most of the mass in an atom. But on the periodic table, you are often given values of the atomic mass. That includes the mass of the entire atom, including the electrons, which although they are small, they do contribute to the atomic mass such that it is different than the nuclear mass. So you'll want to be careful to make sure in this formula that you do not include the atomic mass, but instead include the nuclear mass. For example, if we think about the mass defect in deuterium, which is a hydrogen atom with one extra neutron, we're taking a look at this nucleus right here and the mass defect in that nucleus. And so we could report out the atomic mass of deuterium and subtract away the mass of this one electron here. Or if we're given the nuclear mass, we can just plug that in directly to our mass defect equation. The mass defect of deuterium would involve one proton and one neutron coming together to ultimately create the nucleus of deuterium here. And we were given the nuclear mass, so we can calculate the difference in the constituent particles versus the nucleus itself. And we find that the difference is about 0.002388 U, atomic mass units. Now, I know that seems like a small number that might be rounded off to zero, but with these nuclear physics numbers, we will measure them to a very high precision, so do not round your numbers. Here, this atomic mass difference, this mass defect is to a finite precision, and you must include all values. And if we were to calculate this to the other units of mass that we have, MeV per c squared, we could use that table to calculate the mass defect in terms of those units. Well, since energy is equal to mc squared, and we are finding a difference in mass created when we create a nucleus, there ultimately is an energy associated with that mass difference. And we call this the binding energy of the nucleus. This is the energy contained within the bonds that hold the protons and neutrons together in the nucleus. And we can simply calculate the binding energy for any nuclide as being the mass defect times c squared. In truth, the full equation sort of would look something like this, but of course this is just a substitution of the mass defect equation in there. And so if we just take that number and multiply by c squared, we will get units of energy. So if again we look at our deuterium atom that we just calculated the mass defect for, it had a mass defect of 2.22 MeV per c squared by our calculations. And now this is why you want to leave your units in MeV per c squared. You don't need to multiply the c squared out as a numerical number. It's like a unit, because when you take the mass defect, delta M, and multiply it by c squared, you will get a straight reading of the actual energy. The binding energy of deuterium could be said to be equal to 2.22 MeV. So let's try another practice problem. Let's calculate the mass defect for helium. We've been given some information here, and find the binding energy of the helium nucleus, given that it has an atomic mass of 4.0026 atomic mass units as we read out on the periodic table. So we have to be very careful with the wording here. This atomic mass is talking about the mass of the atom, and that atom does have 2 electrons in there, each with their own mass. It's a small atomic mass and a small mass associated with each of those electrons, but it does matter for nuclear physics. So this atomic mass, we're going to have to remove the mass of the electrons in order to make it a nuclear mass, to make it into a nuclear mass. So let's go ahead and take a look at how we could do that. So here's our mass defect equation, but notice it needs the nuclear mass, not the atomic mass. And the nuclear mass plus the mass of the electrons in this atom make up the total atomic mass. So really the atomic mass minus the mass of 2 electrons will give us the nuclear mass for this helium nucleus. We can calculate the mass defect of a helium nucleus by taking the number of protons, that's 2, times the atomic mass of a proton. Let's go ahead and stick with AMUs for now. That would be 1.007276 U for the proton. There are 2 neutrons as well, each with their own atomic mass of 1.008664 U. Those are the constituent nucleons, the protons and the neutrons. And now we will take our atomic mass of helium. We will take our atomic mass of helium, which we were given as 4.0026 U. And from that, we can subtract 2 times the mass of each electron. The electrons are very tiny, but they do still have an atomic mass of 0.00054858. So there's our electrons there being subtracted from the atomic mass, and we'll find the difference between the nuclear mass in this entire parenthesis on the right, between the constituent nucleons and the nuclear mass. And so here my mass defect number for this helium nucleus, I am getting a result of 0.0304 U. That is the mass defect for this helium nucleus. And I can calculate the binding energy pretty easily if I convert that to MeV per C squared. We'll take that number and multiply by 931.5. That's the conversion between atomic mass units and MeV per C squared. And so this equals 28.3 MeV per C squared. That's the mass defect to put together a helium nucleus. And so calculating the binding energy of this helium nucleus is as easy as multiplying delta M times C squared. My delta M has MeV over C squared. I didn't multiply out the C squared. And so the binding energy in this case ends up being 28.3 mega electron volts for that helium nucleus. We can have a different number of neutrons and protons in specific nuclide variants. If we have an isotope, it might have more neutrons in there, and that makes the nucleus larger overall, or we might have more protons in a certain variant of a nucleus, and that might make the nucleus larger overall and feel a little bit more unstable. And so there is a band of stability where elements will occur naturally, but every once in a while we'll find a variant of the nucleus that is unstable. And so if we are anywhere above this band, outside of this blue line here where we have non-radioactive elements, any of these radioactive elements have the wrong balance of protons and neutrons to be stable. And so this band of stability is nuclides that are temporarily stable, but ultimately the non-radioactive ones that are inert are along the blue line. And we'll find that as we step up to a higher number of protons, as we step up to higher atoms on the periodic table, more neutrons are needed to keep that element stable. It's not a 1-to-1 ratio like you see along this line. As we get larger and larger, more neutrons are needed to actually stabilize these unstable nuclides. And so we would say that certain nuclear variants are radioactive. They break down if they're unstable until they can find a more stable configuration. And some of these radioactive elements take a very long time to break down. we can calculate the binding energy per nucleon, essentially how much energy is associated with the whole nucleus per the number of nucleons that are in that nucleus. And remember, the nucleons include the neutrons and the protons. So we can take our binding energy that we calculated for any nucleus and divide by the mass number, protons plus neutrons, and that would give us a binding energy per nucleon, which you will often be asked to calculate, because this binding energy per nucleon ultimately tells you which elements are the most stable. If there's a lot of energy associated with binding the nucleus together, that means the nucleus is stable and tightly bound together and unlikely to break down. And so depending on the ratio of protons to neutrons, we will have more or less stable nuclide variants. And generally, we can say that things that are above a ratio of 1.5 for protons to neutrons end up being roughly unstable. So there's an energy associated with binding the nucleus together, and the nucleus breaks down into smaller nuclides over time if it's unstable. And this ultimately takes place through nuclear reactions, which alter the nucleus. The nucleus itself undergoes some kind of reaction to turn from one element to another. And in this process of undergoing a reaction, energy will be released or absorbed in that reaction. In general, we can say for any reaction that we will have reactants turning into products and some energy that is absorbed or released in the reaction. The energy that is absorbed or released can be calculated by taking the mass defect between the reactants and the products and multiplying by c squared. So here, if we take the mass of the reactants minus the mass of the products in MeV per c squared, and we multiply by c squared, we will get a heat energy in MeV, and if this Q number is positive on the right side of the reaction, that would mean that energy was released in the reaction, it was given off to the environment, it was exothermic, and if Q is a negative number on the right side of this reaction, that would mean that we lost energy to undergo that reaction. Energy was absorbed by the system. This is an endothermic reaction with a negative Q value on the product side. One of the most common types of nuclear reactions is radioactive decay. Essentially, unstable nuclei will break down to a more stable form through radioactive decay. And in general, for any nuclear reaction, we will always write our parent nucleus as X, turning into a daughter nucleus that also emits a particle and absorbs or releases some energy associated with that reaction. But the different types of particles that can be emitted depends on the nuclear reaction that you're talking about. But in general, since this is our general form of a nuclear reaction, we can also calculate energy that is absorbed or released by taking the mass of the reactants minus the mass of the products multiplied by c squared. And we still need to obey conservation laws in these reactions. That means that energy must be conserved before and after this reaction. So as our nucleus breaks down a little bit, it reduces its overall energy, but at the same time, it emits that energy as some type of particle to conserve the total amount of energy in the beginning and the end of our system. Some other values that would be conserved would be like the charge, the number of nucleons. This is essentially like the conservation of mass. Energy, momentum, and angular momentum will also all be conserved, but one new number that will also be conserved in the nuclear reactions is called the lepton number, which uses script L as its symbol. And sometimes people will call this the electron family number or the electron likeness number. Essentially, we will always have lepton number conserved in a nuclear reaction, so script L of our products will always equal script L of our reactants. This lepton number describes the number of particles in the beginning and the end that have a electron-like nature. They behave like electrons, and it turns out there's some weird particles that come up with different lepton numbers. For example, an electron, which would be written as having a negative Z value with a negative charge and no mass number, would have a lepton number of +1. But there's other particles too, like neutrinos, that have a lepton number of +1. A positron is the antiparticle of an electron. It's like a positively charged electron with the same mass, and that has a lepton number of -1. Same with antineutrinos, another type of particle that we'll talk about in a sec has a lepton number of -1. So if we were to look at this reaction down at the bottom here, where we have carbon-14 turning into nitrogen-14, an electron and an antineutrino, we can keep track of all of our different numbers that need to be conserved. We need to conserve the charge. It looks like I have a neutral atom of carbon here that's got 6 protons. So over on the left side, I have a 6+ in total for my charge. But now for my products, I have 7 protons in this nuclear reaction. So there's 7+ within the nitrogen. And that means that this 1- from the electron charge has to equal across the reactants and products. We have +6 on the left side, +6 on the right side. So charge is conserved. The nucleon number needs to be conserved. Let's check how many nucleons we have. We have 14 on the reactant side and 14 on the product side. The electron is not it doesn't contribute to the mass number. The anti-neutrino is essentially massless. We'll talk more about that in a sec. So we do have nucleon number being conserved. But also we can take a look at our lepton number. Over here, our reactants have a lepton number of 0. No electron-like particles are present in that. It's just an atom itself. And so the lepton number of this neutral atom over here, this nitrogen, is also 0. But what I find for this electron is that I have a lepton number of +1 for the electron and a lepton number of -1 for the anti-neutrino. So the lepton number is also conserved between the reactants on the left and the products on the right. And this is a valid nuclear reaction that could occur. One type of nuclear reaction is called nuclear fission, where we have a large atom that we bombard with incoming high energy neutrons, and those provide the energy needed for that large atom to break apart into 2 smaller atoms, and that's called fission. Some examples of fission reactions are shown here in the box. And essentially, since the mass of the products is going to be less than the mass of the reactants, this fission reaction will always release heat to the environment and create heat. This is ultimately what is used in power plants. We initiate one of these nuclear fission chain reactions where one uranium atom is bombarded by a high energy neutron, breaks that down, giving off more neutrons that break down the next set of uranium within that chain. And we get a chain reaction that can be used to create large amounts of energy, either in like a high energy explosion or in a chain reaction like we would use in a nuclear power plant. All right, so here we have an example of a nuclear fission reaction with uranium turning into barium and krypton. Let's go ahead and try to calculate the energy released in this reaction. We would have Q is equal to the mass of reactants minus mass of products times C². And we were given our masses this time in kilograms, which are kind of inconvenient for nuclear physics. But let's go ahead and see how we can use kilograms rather than AMUs or MeV per C² to solve for this one. And so I calculated my mass defect just fine by taking the difference in the mass of the reactants minus the mass of the products. But now we're in kilograms, and kilograms are actually useful for multiplying C² out with. Let's see how that works. If we have C², that's like 3 × 10⁸ meters per second squared. And we would have a kilogram times meter² per second², which is a joule here. And so the number that we get for our Q in joules is 3.276 × 10⁻11 joules. And then we can easily convert that to electron volt simply by dividing by 1.6 × 10⁻19 joules in every electron volt, giving us a value of 2.05 × 10⁸ eV. And so in terms of mega electron volts, that would be 205 mega electron volts released in this nuclear fission reaction. Another type of reaction that can occur is called nuclear fusion, which is a reaction when 2 smaller elements, nuclei, combine to form a heavier nucleus. And this is essentially what happens in the sun. The massive amount of mass in the sun pulls all the particles together and forces them together so that they fuse into a larger nucleus. And ultimately, we also find that energy is released in this process as well. Ultimately, this type of process is responsible for nucleosynthesis, which is how many of the elements in our universe were created. In the earliest moments of the Big Bang of our universe, small elements fused together and combined to form larger, more complex elements. And then over time, other radioactive processes led to even more complex elements developing over time. Aside from fission and fusion, we can also have other types of radioactive decay processes. There are 3 main reactions that you'll need to know about, really maybe 4 or so, and those are called alpha decay, beta decay, and gamma decay. And these were ultimately named after this because of the order that these were discovered in, and ultimately something about how these different radiation from nuclear reactions behave. Alpha particles have a positive charge and a small penetration distance. So when I undergo an alpha reaction, we emit an alpha particle, and that can barely only penetrate a piece of paper. But other particles like beta particles have a negative charge and a medium penetration distance. So beta particles can make it through a sheet of paper, but not really much farther through metal. And gamma particles or gamma rays can have a very large penetration distance. And this large penetration distance is what causes for gamma rays to have the most energy and do the most damage when they penetrate through our human tissue. So through magnetic measurements, we can determine the charge of these particles. Alpha particles are positively charged, beta particles are negatively charged, and the gamma particles are electrically neutral. Our first type of nuclear reaction is called alpha decay, where an alpha particle is emitted when a parent nucleus breaks down into a smaller daughter nucleus. So here's the general form of an alpha reaction for any nuclide that undergoes alpha decay. We would have a parent nucleus with a set number of protons and mass number, and it would break down by emitting an alpha particle, which is ultimately just a helium atom. We send helium off one way, and what we are left with is a daughter nucleus that has 4 less in its mass number and 2 less in its atomic number. There are 2 less protons and 2 less neutrons, totaling 4 nucleons that we lose. And this alpha decay mostly takes place in heavy, large elements because the nucleus is too large and needs to break down by giving off some of those nucleons. And ultimately, this process ends up being exothermic, releasing heat. Many elements break down through alpha decay because the helium atom, the alpha particle, is very stable. It's an easy thing to exist in nature. And so through alpha decay, we break down large nuclei, which are unstable, sending off a very stable helium atom and breaking down the parent nucleus into a smaller daughter nucleus. But the reason why we don't just send off 1 neutron or 1 proton or 1 electron is because helium is really stable. So it makes a lot of sense to break down a nucleus by sending off a helium atom. So let's go ahead and try this alpha decay reaction for 239 plutonium. It looks like it undergoes a reaction turning from 239 plutonium into 235 uranium and emitting an alpha particle, so we can calculate the heat or energy released in this reaction as finding the mass defect times c squared. So here in this reaction, I calculated the energy released as being 5.245 MeV. And notice that we started off with atomic mass units here. We can run this mass defect calculation with kilograms, AMUs, or MeV per c squared, as depending on which numbers we've been given. And you can always convert from atomic mass units to MeV per c squared by multiplying by that conversion factor. And so you'll want to get used to switching between these different units. The next reaction we'll learn about is called beta minus decay, where a beta minus particle is sent out after this radioactive decay process. This one's a little bit trickier than alpha particles, but essentially one of the neutrons in the nucleus is broken apart or converted into a proton, an electron, and this particle called an antineutrino. And an antineutrino is a massless particle that essentially keeps the energy conserved in this nuclear reaction. In general, the neutron breaks down into a proton, an electron, and an antineutrino, and we know that particle must be there to conserve the energy. And so for beta minus decay, the general reaction is shown here, where we have a parent nucleus with mass number A and atomic number Z, turning into a daughter nucleus with 1 more proton and 1 less neutron to keep the mass number the same in the end, sending off an electron, which is a beta minus particle, and an antineutrino, which we use the Greek letter nu, looks like a cursive V with a bar over it. We contrast beta minus decay with beta plus decay, which sends off a beta plus particle. This is essentially also known as positron emission, and this is kind of like the inverse of beta minus decay. We're taking 1 proton and turning it into a neutron and a positron while also emitting a neutrino. A positron is the antiparticle of the electron. It's like the inverse of an electron in nuclear physics. It's got a +1 elementary charge value, but no mass number, and it has a positive electrical charge value. Keep in mind, the positron does have a lepton number. It's an electron-like particle with a lepton number of -1. In order to maintain that lepton number, we need another particle with another lepton number, and it turns out that that is a neutrino with the Greek letter nu. no bar over it. And this is basically a massless particle with a lepton number of +1, such that we can keep everything conserved for any beta plus decay reaction. A proton breaks down into a neutron, a positron, and a neutrino. And so the general reaction for beta plus decay looks like this, where we have a parent nucleus with mass number A, atomic number Z, breaking down into a daughter nucleus with one less proton, but one more neutron, maintain the same mass number. And we also emit a positron and a neutrino. In any of these reactions, you can always check to make sure that your values are conserved. Here, we have one less proton, so it's like we have one less plus, but that plus shows up in the positron to keep the whole reaction electrically conserved before and after the reaction. Similarly, we could calculate our lepton number. Our neutrino has a lepton number of +1, and the positron is an anti-electron with a lepton number of -1. So in outer space or in some nuclear reactor where we have beta plus and beta minus reactions happening, an electron and a positron will both be floating around in that system, and eventually those two will recombine or annihilate. And when an electron combines with a positron, essentially what we create is two very high energy photons that go outward in opposite directions. Two electrons come in, crash together and annihilate, and send two photons out in opposite directions. The energy of a gamma ray in this annihilation reaction can be said to be equal to 0.511 mega electron volts. Another way that we can generate gamma rays is through gamma decay, and this is what happens when we have an excited nucleus in a high energy state that needs to relax down to a lower energy state. We know in quantum mechanics, when a quantum mechanical object is at a high energy and goes down to a lower energy, it emits a photon equal to the energy of that transition. And so for gamma decay, we could take our parent nucleus, which has a mass number A and atomic number Z, and it turns into a daughter nucleus with the same mass number and atomic number, but in a lower energy state. And in that process, we emit a gamma ray or a photon with an energy that matches the energy of that transition. So another type of reaction we can have is electron capture, where a parent nucleus captures an inner core electron from another element and ultimately leads to a daughter nucleus that has one extra electron and also emits a neutrino. This electron capture process can ultimately lead to something called an X-ray cascade, which allows us to create X-rays where electrons in higher level orbits will cascade down and jump down to lower energies, emitting characteristic X-ray photons that match the energy of those transitions. So in a nuclear reaction, the radioactive activity A determines the rate at which reactions occur. Activity is measured in decays per second. It's the number of reactions occurring over time. It's essentially gonna mean that our number of nuclei that we have will decrease as time goes on. And we can calculate this as an exponential decay function with a rate constant lambda times the number of nuclei present at any time. As we have more nuclei present, we also expect for our activity to increase. This is because the more stuff that we have, the faster the reaction will occur. That's how exponential decays work. And this activity can be measured in decays per second, which is given the unit of Becquerel, the scientist who was researching radioactivity at the time. But this also can be presented in units of Curies, which are Ci, and you can relate that to the number of becquerels or decays per second through this conversion at the bottom. The radioactive decay law explains the exponential decaying nature of nuclear reactions. Essentially, the number of nuclei at some time can be said to be equal to the initial number of nuclei at the start of that time interval times the exponential raised to the power of negative lambda t, where lambda is our rate constant measured in inverse seconds. From what we learned about exponential processes in the past, we know that the rate constant of an exponential decay process is related to its half-life time, and we can calculate a relationship between the decay constant and the half-life time with this equation down at the bottom. So sometimes you'll see the radioactive decay law shown in its full form with the half-life time present in there as well. We note that when we allow for the reaction to occur for the amount of time that is the half-life time, that the number of nuclei will decay by 1/2 after that time interval. Okay, so here we are asked to calculate the activity in a carbon dating application. So here we have carbon-14 given with a half-life of 5,730 years. It's going to break down to carbon-12, the most stable state. And we want to see what the activity is of a 1 kilogram sample that contains carbon-14 in an abundance ratio of 1.3 carbon-14 atoms to every 10 to the 12 carbon-12 atoms. So this is like a ratio that carbon-14 occurs at with respect to carbon-12. So first, we're going to want to think about our activity equation. Our activity is equal to the rate at which nuclei break down over time, but we don't have that information. What we do have is something about the rate constant and the number of nuclei present at this time. Calculating lambda is as easy as taking the ln of 2 and dividing by the half-life time. So that would look something like this. And we want to make sure that our rate constant is given in inverse seconds. So that we'll take our years and we'll convert those years to seconds first. And then we'll calculate lambda from there. And so for my lambda number, I am getting a rate constant of 3.8 times 10 to the negative 12 seconds to the minus 1. That's my rate constant lambda. And so now I'm going to need to calculate the number of nuclei present in this 1 kilogram sample. So if I have 1 kilogram of this living sample and I want to convert it to moles or grams, there are 1,000 grams in every kilogram. Using the periodic table, I can figure out how many moles of carbon-12 that would be. And so in every 1 mole of carbon-12, we have 12 grams just about. That's from the periodic table. That is our molar mass of carbon-12. But we know that for every mole of carbon, for every mole of carbon-12 that we have in this sample, we have Avogadro's number of nuclei. That number of atoms each have their own nuclei. So there are 6.0 times 10 to the 23 nuclei of carbon-12 in this sample that we use to calculate the molar mass from. And lastly, we know that for every 10 to the 12 carbon-12 nuclei that we have, the percent abundance, that abundance ratio, will mean that we have 1.3 carbon-14 nuclei. And that should tell us how many nuclei we have present of carbon-14. The number of nuclei we can calculate. And so the number of nuclei is 6.5 times 10 to the 13 carbon-14 nuclei. And so that number really is just a unit to keep track of a count of nuclei. And if we wanted to calculate the activity, we could calculate it by taking our rate constant, 3.8 times 10 to the negative 12 inverse seconds, times by the number of nuclei that we have at this time, 6.5 times 10 to the 13 carbon-14 nuclei. And so here I'm getting an activity of 247 decays every second. That's the number of nuclei times the rate constant. And so we could also say that this is something like 247 BQ. So it's all starting to come together. Our knowledge of quantum physics, the periodic table, and everything that we've ever done in physics class has led to this moment. I hope it's making sense for you. Make sure to engage in the content in the coming days. Thanks for sticking around. I'll see you in the next one.